Let me go back. So before starting, who can tell me what process is? Yes. Yes. Yeah, exactly. So process is exactly program in motion or a program that's currently executing in the system. So from one program, you can make infinite number of processes, obviously. You can run it multiple times. Can you tell me some, so let's say if a program is just a bunch of code, lines of code, right? And the process is those lines of code that are getting executed. And can you tell me some other properties that a process might have? Yes, exactly. It would have that. It would also have memory, right? It will take some memory from your CPU. Actually, it's gonna get executed in the CPU, and it will take some of your main memory while it's getting executed. So yeah, good. So you know what a process is, great. Now let's dig a little bit deeper into that. So as you all said, process is a program that is currently getting executed. A process is an active entity, something that is active. Program is a passive entity. It's just code, right? So in some systems, you can call the process jobs, okay? But normally the process and job are used interchangeably, okay? So if you read books related to operating systems, to computer science, sometimes you're gonna find the word process, sometimes you're going to find the word job. It is pretty much the same thing. In most cases, when you're doing, for example, let's say you have a virtual machine on which you want to execute some project, right? The execution, normally we call it a job. We don't call it a process, okay? But again, they are used interchangeably. Okay, so as we mentioned already, the process have multiple parts. So obviously, the program is just a text section, right? So it's just a bunch of instructions, whether it's on C, on Python, or any other programming language. The process is, on the other side, taking a little bit more resources from your computer, okay? So there are a few things that the process have in addition to the instructions. So it has a stack, okay, where it stores temporary data, okay? It has data section where it contains some variables that are needed for the program to execute. It also has a heap, which is some memory that is dynamically allocated to this process. Okay, so for example, if you want to run a program into your computer, so you have a process, let's say if there is a function code inside this program, okay, this function will dynamically get allocated, and some of the variables of that function is gonna get on the stack, right? And so on. So normally, how do we start a process? So there are actually three ways. One of them is automatically, so obviously when you start your computer and the operating system starts, there are some processes that are running on the background, right? Also on the other side, you can start it, you know, it's very easy. From the user interface, you double click on executable file, and you start a program, or the program gets executed as a process in your computer. The third way is to use a graphical user interface. Actually, the third way is to use a command line interface, which is pretty much you write some command. Let's say if you want to run a Python program, you're going to write Python and then the name of the executable file. If you want to run a Java executable file, you can also write a Java, and then the file that is related to Java will get executed. So you can see here how a process gets stored in the memory. So you can imagine this as a piece of memory on your device, and you have some part allocated for the heap, some part allocated for the stack, and also for some additional data that your process needs to execute. So, I'm guessing that in your other classes, you've been studying about state machines, right? Who can tell me what is a state machine? It's actually something pretty simple. So a state machine, you can imagine it as different boxes. Each box represents a state, and it just shows from which state to which state you can go, okay? The same thing is with the processes. So every process can have multiple states, right? When you create a process, we have the state new, right? So the process created, but it haven't been yet executed inside your system. So I have the following question. Do you know what is the system call with which you can create a process but not execute it? So my question is how you can create a process. For example, let's say in Linux, what is the system call for creating a process? Any ideas? For sure you've heard it. Okay, so to create a process, you usually use the fork system call. Okay, so when you perform the system call fork, you create a new process. This process is not yet running. Okay. Now the other state is obviously running, and this is when your process gets actually executed in the system. So now it gets to the CPU, and the CPU starts processing it, right? Then you also have the waiting state. So the process can be waiting for some state to occur, right? Many programs are running multiple processes, right? So for example, if you run an IDE on your device, let's say PyCharm or Visual Studio and so on, there are many processes running in the background. So sometimes one process needs to wait for another one to complete before to start, right? Then you have, exactly. So the processes, they are written in different programming languages, right? So process is actually a program. So let's say if you want to execute something that is written on Python, okay, when you run it, it becomes a process on your computer. Pretty much that's it, right? Okay, so waiting means your process is waiting for some event to occur. Then ready means that the process is waiting to be assigned some resources from your CPU, right? So it's waiting to be executed, okay? And I know that, okay, you're going to tell me the state ready with the state waiting with the state new, they might be a little bit similar, right? But you're going to see in a second what's the importance to have those different states. And obviously terminated means that the process gets destroyed, okay, and removed from your CPU and so on. Okay, so this is what I mean by state machine. So this is pretty much the life cycle of the process. It gets created, okay, then it becomes ready after it's been created, okay. So we need to do some verification before putting it as ready. And after that, we can run it, okay? Once we run it, it is possible that at some point we start running the process, but before finishing it, okay, we need to wait for some other event to occur. Then you can go into a waiting state, right? Waiting. After waiting, it can become ready again. And as you can see here, once the process is terminated, there is no way back, so the resources, they're released. And if you want to execute the same program, obviously you need to create a new process with new resources. Okay, so every process has a process control block, okay? So those are some characteristics related to the process that are important and are specific for each and every of those processes. Now, those are some of the parameters that are involved in the process control block, okay? So the first one is the program, is the process state, as we said, running, waiting, and so on. Then we have the program counter, which shows the next instruction to be executed, right? So for example, if your process prints hi and buy, while you're running the command high, then the program counter points to buy, so you know that this is the next instruction to be executed. Okay. Then we have the CPU registers. Okay. And obviously this is self-explanatory. This is the register that is actually executing the process inside your CPU. Okay. Then you might have CPU scheduling information. Okay. So for example, if your process needs to wait for something to happen, or something needs to wait for this process to happen, then this information will be stored in the CPU scheduling information. Okay. Then another thing that a process would have is how much memory is it allocated to it in order to be able to execute properly. Okay. So you can also have accounting resources, and accounting resources is pretty much some information about the process. So at what times it runs, okay, to keep track on the time, to keep track on the CPU resources used. This is something very important, because if you have a process that uses too high percentage of your CPU, you want to know about it, right? And finally, there is some information about the input and output devices. Obviously, some processes, they use your monitor, they use your keyboard, they use some external hard drives. So this is also important information that we need to store. All right, so we're just briefly going to talk about threads. We have a whole lecture about threads, but who can tell me what thread is? Any ideas? Series of steps. Okay. Any other ideas for threads? Yes, 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 pretty close. So yeah, a thread is obviously many processes running concurrently, okay? Or also you can have multiple threads within the same process. So you can imagine, let's say, I want to run a program that want to show the time, and at the same time, I want, let's say, I want to see the time at Fitchburg, and I also want to see the time somewhere else, okay? And I want to run one program to do that, okay? So obviously I will need two threads. One is going to run some code that will show me the time here, and the other thread is going to run some code that will show me the time somewhere else. They need to be working at the same time. So we no longer just take the lines of code step by step, okay? But we take some lines at the same time. Okay, so you can have as many threads as you like. Another example of threads is, for example, when you open your browser, you can open multiple tabs there, right? Not only one. So you can imagine that each tab is a thread. So you want to have multiple pages able to be used by you at the same time. All right, so here is just a little bit more practical representation on how the process resources look like, for example, in Linux. So when you execute process in Linux, you use the file task struct. Okay, so when you build, imagine when you build a process, you call this file task struct, okay, and then you use the program code, okay, you add it in the task struct, and from the program you create a process that is running. So the task struct, for example, is adding those parameters, okay, to your script before executing it in the memory. So pit, hello, yeah, come in. So first of all, we have the pit. Who can tell me what pit is? A process identifier. Okay, it's written. So this is some unique number that is related to the process that executes into your device. I think I showed you last time, but for example, if I open a terminal, right, and I do PS, okay, it will show me processes that are executed right now. For example, here, in this terminal, I can see the process that is responsible for opening the terminal and allowing me to write commands. Okay, so this is the process, and this is the ID of that process, right? So let's try another thing. So if I want to, if I add PS here, you can see that even though we open exactly the same programs, okay, now we have them under two different processes, right? So this is the type of the program, okay, this is the window. However, we have now two processes with two different pits, okay? So this is pretty much how you can see the difference between a program, okay, and program executed as a process. Okay, so other than the identifier, you can see that we have encoded here the state of the process, we have the scheduling information, we have the process parent, so obviously, and we're gonna go over it, every process can have children processes, right? So you've heard about the relationship parent-child. So a process can obviously create child processes, and here we're going to keep the information about the process children and the process parents, okay? Then if the process needs to access some files, here we have list of files that the process can open, and also here we're going to have the address space of the process, so where the process is located. So for example, let's say if we have a process that we want to convert from one state to another, okay, let's say the state is ready and then we want to execute the process. So what we're going to do, we're just going to change this current pointer from the previous state to the next one in our possible states. So it will be something like current state is equal to the new state. So we're just going to move the pointer to the state that we desire. By the way, do you see your name right there? Because I'm recording the people who came today. Which number? 10? Okay. 10? This is the one? Okay. I have a question. Did you think the lecture starts at 5:30 or you know it starts at 5? Ah, you know, okay, good. I'm just checking because sometimes maybe students got confused because of the first lecture, but okay, good, good. Okay, so now, when we know what a process consists of, now let's talk about how we schedule them, okay? So how do we decide which processes should we execute and which should we put to wait a little bit, okay? So to do that, we're having schedulers, okay? So in the operating system, there is long-term scheduler, short-term scheduler. Those schedulers, they are managing which process is going to be executed in the CPU and which process is going to be waiting to get executed. So before talking about the schedulers, firstly, we're going to explore the different queues that we have in operating system. So first of all, we have the job queue, which is the queue of all of the processes that exist in our system. Then we can have the ready queue, which is the queue with all the processes that are ready, okay, that are in the main memory and are waiting to be executed, okay. Then we have the device queues, which are the processes that are waiting for some device to become available, okay, or they need some device in order to be able to get executed. So every process migrates between those different queues. So how we implement the state machine that I showed you earlier is by putting these processes into different queues, so they're waiting for their turn, okay? Okay, and this is how a typical queue looks like. So normally we have the head of the process pointing to the next one and the tail pointing to the last one. And here is how the whole tree looks like. So let's say we have the CPU right here. So if the process goes to the CPU, it gets executed in the system, right? So the rectangulars represent a queue, okay, while the circles represent processing units like input-output devices, child process execution, or the CPU. So what happens is that every process, let's say I create a process that needs to display something on the monitor, right? So obviously this process firstly is going to go to the input-output request queue, okay, and is going to be waiting for the monitor resource to be available. Once the monitor resource is available and we can now access it, then the process is going to jump to the ready queue, ready to be executed for the CPU. We need to do that because we don't know, or the process doesn't know, how loaded the CPU is. If the CPU is too loaded, we're just gonna stack processes right here in the queue that are going to wait to be executed. That's why when you execute too many programs in your computer, when you open too many tabs on your browser, and you don't have enough main memory to support those processes, or your CPU doesn't have enough cores in order to execute those processes, your computer gets slower because the CPU starts throttling, meaning that it reached its maximum, so more processes get here on the ready queue and they're just waiting, so everything starts feeling slower. Alright, so once we know now about the queues, we can actually talk about the different schedulers. Okay, so in the system we're having two main types of schedulers. Actually there is a third one, but for it we're going to talk a little bit later. So first of all, the most important scheduler for every operating system is the short-term scheduler. So the short-term scheduler executes processes every 100 milliseconds. Okay, so you can imagine every 100 milliseconds a new process goes in it, okay, and it gets executed. So let's say if the time that takes for a process to get to the queue and to get to the scheduler, so if this time is 10 milliseconds, this means that 10% of the work is done just to schedule the process and 90% is done for executing the process itself, right? Okay, so this means that the short-term scheduler, obviously it comes from its name, it is used to run processes frequently, okay? So now, the other thing we should mention is that the short-term scheduler runs the processes into the CPU, right? So it takes them from the main memory and then puts them in the CPU for execution. Now, the long-term scheduler on the other side, it is taking the processes and puts them, okay, to the ready queue, okay? So it puts them in the main memory. So the long term puts the process in the main memory, the short term takes them from the main memory and executes them on the CPU. Not all the systems actually have long term scheduler, right? Some of them, they're just taking the process, the short term, so they just have the process in the main memory and the short term takes them straight to the CPU, okay? So the long-term scheduler is executed, let's say, every second or every few minutes. It takes way longer to pick the correct process to be loaded into the main memory, okay? So it takes more time. Normally in the systems, if we take all the different types of processes, we can divide them into two main groups. So processes that run on input or output devices, or processes that run strictly on our CPU. Okay? So a good scheduler is going to take a good mix of both of those processes. Because if we have, let's say, the CPU bound processes with priority, then maybe some of the things that use input output devices will not get ever to the CPU, right? So what we want is to have a very good mix of both of those. Okay, so today pretty much most of the systems are also having medium-term scheduler. Okay, so the medium-term scheduler is doing swapping. And you can imagine this as, let's say, you're waiting on the queue inside the grocery store, right? So imagine you just go there and you're getting just a milk. You go to the cashier and you see that there are so many people waiting on the line with, they're full of groceries, right? So then some of those people, or even the cashier, is telling you, hey, you just have a milk, so come here, I'm going to serve you so you can go faster because it's just going to take me like 1 second. Why should you wait for so long time? This is exactly the role of the medium-term scheduler. So what it does, when you have a process in the CPU that is known to be executed for longer time, the medium-term scheduler takes this process and it saves its state, it saves all the variables and parameters at the point that the process was swapped, okay? So records the state. So the CPU can get free up and execute those faster processes quicker, right? Just in the same way. So once the scheduler takes that, it puts it back to the ready queue with the state variable marking until what point the process was executed, until what line of code we executed this process. So once now the CPU is a little bit more available, the CPU already executed the faster processes, then the CPU can again take and finish this previous process. This is something that really improves a lot the work that computer is able to perform. Okay. Any questions so far? Okay, is it clear for the medium-term scheduler what it's doing? So if you heard about swapping, this is exactly how it is actually done. Yeah, and this is exactly what I was explaining, that we save the state, right? And after we start the process again, we started from the save state, so wherever work was done, we can actually continue it. All right. So the next thing we're going to talk about is going to be about some of the main steps throughout the life cycle of the process. So those are the process creation, process termination, and so on. Okay, so first we're gonna go to process creation. Okay, so here's where we're going to talk about parent and children processes, right? So who can tell me what is a children process? I already said that. Yeah. Can a process be parent and children process at the same time? Yeah?
A process can create a process that in turn creates another process.
Yeah. Okay, so if we have a children, then can a process have grandchildren? Yeah? Yes, yes. So we can have grandchildren, grandchildren, and so on. Okay? So you can imagine the creation of processes as a tree, right? So you can have one process on the top, and then from there you can have as many other processes as you like to. Okay? Now, there is one very important topic here when we create children, process children's. So from where the child takes memory resources? Do we allocate memory to the parent and then the parent gives those resources to the child? Or are the childs having just a completely different resources from the computer? It depends. Yeah, exactly. It depends. We can do both. Okay? So if the child has independent resources, then what is the risk? So if the child has independent resources, this would mean a parent process, we can do for I in range 1 billion, run this process, right? So then we're gonna run 1 billion child processes that will take resources from your computer. They're not part of the parent, so we don't have dedicated resources for them. They're just gonna take everything possible, and they can block your computer. On the other side, if the child shares the resources with a parent, what we're going to do, when we create a parent, we'll say, okay, you're taking that much resources and you can share them between your children and grandchildren as well. Okay? Also, the parent and the children can either execute at the same time, or there are some processes that can create children process and just wait for them to get executed. Once all the children processes get executed, then the parent process can resume execution. Okay? So both of those ways currently exist. And here you can really see a complete tree. So this is in Linux, right? So we have the init process that initializes the system, sets up all the drivers, registers, and so on. And then from the init process, we can call the login child process. We can call the SSH, okay, which is for secure login. We can call bash, which is program that is used to create scripts, okay, and it allows you to write in the shell. The ps command that I just used, the Emacs, which is a text editor just like Word. This is just used in Linux, and so on. And it all comes from the init. So this is how the process tree looks like. So the child process, we can choose, it can be a duplicate of the parent, or it can be a completely new program. Okay? And here is actually the scheme down there to see how a parent can actually wait for a child to complete. Now, let's say we can do the fork, so we use fork 4 to create. Say again, sorry? Yeah, give him a hint, yes. You're not sure? Who can tell me what we use fork for? Yes?
Create processes.
Exactly. So we use the fork system code to create processes, right? So let's say we create a parent process, and at the same time we create a child process, right? So this is just one of the ways to do it. So we create both, and then the parent goes into the wait state. So we saw that we have the wait state. So when a process is in wait state, it waits for something to happen, right? So our parent process can wait for the child process to complete, right? So we start the child, we execute it in the CPU, and then once we exit from the child process, we return back to the parent process, and then it can actually finish. Yeah, and this is exactly what I just mentioned, right? So let's say we're using the exit keyword, right, to exit from the process, and the parent can wait for a child using the wait system call. Now, there is also another way to end the children process, and this is to abort it, okay? Every good operating system has abort functions, so the parent can actually stop the child unexpectedly, right? So the parent might do that if the child exceeds the resources that were allocated to the child process, okay? the parent can also abort it if the task that is assigned for the child is no longer required. We no longer need it, so we just stop it, right? Or the child can be aborted also automatically if the parent gets terminated. But actually this is not always the case. Okay, so sometimes if you create a program that creates a parent process and the parent process waits until the child completes. So what happens, okay, if the child never completes? This means that the parent process also never completes, right? So the parent is always going to run this wait system call and it will never finish. So it will become a zombie process, right? So it will be in the system, but it is going to wait for the child, okay? Sometimes the parent process can get terminated without invoking the wait system call, okay? And if in the system we're waiting for this process to get terminated and for the system call wait to be invoked, okay, then the system will never know that the parent has actually been terminated. So then this process is going to become an orphan. So it's going to be always there in the background and there is no way to stop it. For this reason, many operating systems are having specific functions inside their initialization programs that are stopping both of those types of processes. Or they have functions that run periodically and they look for those type of processes and kill them. Okay, this exists also in today's systems as well. And this is actually something that we talked about in the beginning of the class. So here is a very interesting example with a browser, right? We're talking about browser running in different threads, okay? But also there is an interesting example of the Chrome browser, how it uses different processes for some of its functionalities. So in the past, obviously the browsers, they had only one tab. You couldn't create multiple tabs. It was only one. This was because the whole browser was just a single process, okay? So this means that if the browser would have multiple tabs, if one of the pages crashes, then the whole browser will crash as well. These days, for example, Google Chrome, it's done in a completely different way. So when you launch the browser, you start the browser process, okay? That is doing the user interface, okay? It also connects to the network and so on. You can access internet from it. Also, when you start a browser, you might heard this term, you're starting a session, right? So session is at browser level. It's very hard actually to exit a session, especially in Google Chrome. The only way if you want to exit a session is to create an incognito window, right? Otherwise, they have now connections between the different windows, even if they're not on tabs, right? And they always have your data, or they always have your account over there with cookies. So this is just an example. Now, so we start the browser process. Then when we open each tab, we're having a renderer process. So each tab is renderer process. Our renderer process is responsible for dealing with HTML, which is what is HTML? Okay, yes, and it's used for what? Yeah, okay, so it pretty much, this is the front end of the pages in internet, right? From the AI class, we do that, correct? Yes, and you've also been there last year, so you know. Yeah, so the HTML, yeah, you don't know? Yeah, he's been in the, okay, okay. So, HTML, JavaScript, CSS, all the code that is responsible for the web page is executed by the renderer process. So if this code fails, what happens? Only the tab fails, but the browser is always on. Okay, and finally, we have another process for the plugins. So you know that browsers these days, they all have plugins, right? So the plugins are also run in another process in the background. So those plugins are applicable to all the pages, but they are independent from the browser. Why? Because we don't want our plugin to crash the browser. So this is why today's browsers are that stable, because the browser process pretty much nothing happens there. It just runs in the background and makes sure that your browser window is all set so you can see the rest of the tabs. Okay, so now some of the processes on your computer are running as independent, right? They are not depending on any other processes. They don't need to communicate, okay? But some of them are called cooperating. Cooperating means that a process wants to communicate with another one to achieve certain goal, okay? And why would we want our processes to cooperate with each other? Well, the reason is, so I put 4 reasons there. Maybe you can find even more, okay? So they might just want to share information, right? So let's say if you log into Word and Excel, in between them, they're going to share information for your Microsoft profile if you're logged in, right? So some applications might need to exchange information, okay? Then we might use cooperation between processes to speed up a little bit the tasks that we want to complete. For example, if you have a network of computers, they might want to exchange some of the processes that are running on them, because let's say one don't have enough resources, right? So it wants to send it to another one. Or even on the same computer, two processes, they might share some different locations on the CPU, and when once one is a little bit overwhelmed, it can pass the tasks to the other one. Okay? So how are we implementing processes that are communicating? There are two ways. The first one is called share memory, and the other one is message passing. So, without showing you what the next slide looks like, what do you think means shared memory when we want to communicate between two processes? How two processes might communicate with shared memory? What do you think? Yeah, exactly. Yeah, it's very logical actually, yeah. So this is explained with a simple words. This is exactly what it is, yeah. Now, the other one is called message passing. So how to process communicate with message passing? What do you think? Yeah, or messages, right? Actually, when you exchange a file, you're actually exchanging messages. This file is broken into different messages, they are transmitted as signals, and then they arrive to a certain location. So yeah, exchanging messages, files, and so on. So those are the two ways. Let's see now how are they implemented. So you can actually see both of them here. Let's imagine that this is the shared memory. So you have process A, process B, and you have some memory location, and one process can upload things there, and the other one can use those things and take them, right, from this memory. The other one is process A and process B. They put messages in some message queue, okay? And let's say A puts messages in the queue, and B takes them and uses them for whatever reason process B needs. Okay, so you remember in our first lecture we were actually talking that it is not really the best thing for processes to share the same memory, because let's say if one process updates this memory and then the other process is looking for something that is not there anymore, we might have failures, right? So if you want to do memory sharing, we need to forget about this rule, okay? So we cannot follow it anymore, which means that we need a very good synchronization between the two processes that share the same memory, okay? So when we share a memory, you can imagine this as a buffer. Buffer is a space where you put information, okay? A good practice is for this buffer or this space to have some limit, okay? So we have two choices. The first one is the buffer to have a limit, and the second one is the buffer to be able to extend without any sizing. Of course, it's not that preferable because the buffer will have in that case unlimited size. So this is a very simple code on how we can actually implement shared memory. Okay, so you can see here we can create a buffer, right? And once we create a buffer, we can have two pointers. So let's say the in is going to point to the first empty element, and the out is going to point to the first element that has some information on it, okay? So we will know at any time which part of the buffer is empty and which part of the buffer is full, okay? So let's say if we have two processes, one of them is producer and the other one is consumer, this means that the producer process will put things on the buffer, while the consumer process will take things from the buffer, right? So the producer will not put anything on the buffer if the buffer is full, okay? So let's say if this is the rule of our buffer to be full, then if this is true, okay, we're not going to do anything, right? But if it is not, we're going to take the first empty location, okay, and we're going to put the next produced item on that location. After that, we're going to move the location to the next element, and we'll keep putting elements on the buffer until we're done with that. So this is how it's implemented, a producer process, okay? Now the consumer process is also very easy to understand. So if in equals to out, this means that our buffer is empty, okay? So there is nothing to consume and we're not going to do anything. If this is not the case, okay, we're going to consume the next element, okay, that is available on the buffer, okay? And after that, we're just going to move to the next one. So this is pretty much, you can see it's maybe about 15 lines of code, how you can create easily a buffer and consumer that can share the same memory. Okay, so obviously when we have shared memory, one very important thing is to have a very good synchronization between the processes, because we don't want the consumer to go to the buffer and try to get something that is not there. Yep. So let's say if you have one variable and if you want two processes to access this variable at the same time. Okay, yeah, good question. So first of all, if you don't, you don't necessarily need to remove the variable in order to read it, right? So one way might be to create a copy of this variable, okay? So you have two copies and the two processes can access it, right? This is one way. So for example, in which programming language are you asking for? In Java? Okay. Okay, so let's say we take yeah, so okay, let's say we take the example with Python, okay? So in Python, obviously Python is interpreted language, right? So it runs way above the operating system, so it's a little bit easier. So there, let's say if you create a variable, okay, and later in the code, let's say you create two threads, right? So both of those threads, if the variable is in the outer scope of the threads, So let's say first you define the variable, okay, and then you have two functions that run at the same time. So you create function 1, function 2, and after that you create a new thread. First thread is running function 1, second thread is running function 2. Okay? Since the variable is defined globally, obviously it will be accessible from both functions that are running, or from both threads. Yeah, yeah. In Python you can use the global keyword, for example. I'm sure in Java there will also be a way. Yeah. Uh, yeah, it is possible. Yes, two processes they can access the same place. Yeah, yeah. Like in the Python, you can imagine this. For example, I put something on a memory location, and nothing stops two programs to have pointers to that location, right? Yes, yeah, yeah. It really depends. To be honest, let's say if you store them at the same location, right, and both of them want to access it at the same time, obviously there will be some delay, but on the computational, based on the computational power, you're not going to feel this delay, right? It's not going to be something significant.
But we cannot say both threads can access that variable in the same time.
Yes, yes,
There might be some delay.
yes, yeah.
There should be some delay.
It should be, yes, yes, yes. It should be some small delay, of course. It's not going to be significant, but obviously, if you're making multiple functions in that program to add this delay over and over again, yes, it might lead to something a little bit more significant, right? Okay, so this is how you can assess, and you can communicate between two processes using shared memory. And the other way, as I said, is message passing. Okay, so message passing, you can imagine this as two functions, right? So we have the send and the receive function. So let's say I can use the send function to provide some information about the process to which I wish to send something, and then I can also provide the message that I want to send, and then I will send it. Then the process that receives information, they can have the receive function, okay? So then they're able to receive messages from somebody else, right? Okay, so when we are sending information from process to process, okay, we need to establish a link between them, okay? So obviously, let's say if I'm speaking to you right now, I'm delivering you the message that I'm speaking, but in order for you to get it, we need to have some link in between us. So our link right now is the air. This is the link. If I speak to you in the space, you're not going to hear me because we don't have the air that transmits the sound waves, correct? Okay. So it is the same way when we want to talk with two processes. They need to have some link, right? They need to be able to access each other. So the link they can have by having each other addresses, right? So in order to process to communicate with each other, they need specifically one link associated with them. If you have more links, things might get a little bit more confusing. And we actually don't need more links. Now, this is how you can actually send messages. For example, if there are two processes, P and Q, right? On the side of Q, we can have this send function, and we can set the message to process P. So we're going to specify the location of P or the name of P, however we write the function, and we can specify the message. Then we can also specify at the P side, right, a function that is able to receive messages from Q. Okay, so we can establish a link between them, and then they can start sending messages to each other. Okay, so this is just one of the ways, the less preferable way. The other way to exchange messages is to actually put them into mailboxes. So process P no longer wants to send message directly to Q, but instead it wants to put it in a mailbox. So the idea here is that, let's say, me and you, we want to communicate, right? So what I'm gonna do, I'll give you the address of some mailbox that is located in the desert or somewhere else, right? And both of us, we will know the address of this mailbox. So I'm just gonna go there. I'm gonna put you a letter just for you, and just because you're the only one that knows this mailbox, then you can receive it, right? So that way we can also have other processes as well to be able to read the information from that message. They just need to open the box, read the message as well, and that's it, right? They can all access it. So this is way better because we can use one link for the communication of multiple processes at the same time. So here are the operations that we're going to do. Firstly, we're going to create a new mailbox, okay? And addressing within the operating system can be done by port, okay? So create a mailbox, we're going to provide the port, which is going to be the location of the mailbox, okay? Then we can send and receive messages through this mailbox. And finally, once we no longer need the mailbox, we can destroy it. Okay? So here our send and receive functions change a little bit. So first of all, the send function is going to send messages directly to the mailbox A, right? And also the receive function will actually be able to receive messages from mailbox A, right? So here we have just one location which we worry about. Also, this technique helps us to reduce the hard coding in our operating system. Hard coding means specifying specific processes manually that should communicate with each other. We no longer need to do that, right? So when the process needs some information, it can just have the address of the mailbox and check there. Okay, so as we were talking, in order for process, for example, to share the same memory or even to send messages, they need to be synchronized, okay? So we have 4 different types of processes based on synchronization. So first of all is called blocking send, okay? And this is when a process, once a process sends information for another process to read, this process gets blocked or stops working until the other process receives the information, okay? Then blocking receive is when a process waits for some information to be received and stops working until it doesn't get this information. And this is an example of synchronous blocking, right? Now, when we have non-blocking, we call this asynchronous. So what happens then? We are sending the information, but we continue execution even though we don't know whether this information has been received or not. And this also accounts for the non-blocking receive, right? So we expect some information to be received, but we continue running the program, okay? Even if the result is going to be no. Okay, so for example here, you can see an example of produced and consumed message, okay? So we can do while true, okay? Send the next information, right? So we can send the next thing that have been produced, the next message that have been produced from us, okay? So we constantly emit information. And we can do exactly the same right here, okay? And finally, there is also a few types of buffering, okay? So we know that when we share memory, we can imagine the memory as a buffer, which buffer gets filled. So buffer have different locations, and it gets filled with information, and then another process can take this information. So we have 3 types of buffering. The first one is the zero capacity, okay? So in that way, we actually don't really have a buffer, right? So the sender should wait for the receiver to be ready to receive the information. We cannot store it somewhere else while the receiver is doing something else. We can have bounded capacity, where we have a finite length of the buffer, and once this length gets completed, the messages start queuing, right? And finally, the unbounded capacity is when we have unlimited buffer. Of course, there is never unlimited, but we don't put specific restrictions, so the sender never waits for a message to be delivered.